And joining us this morning from aboard Columbia, our mission specialist, Mike Gernhardt, and payload specialist, Roger Crouch. We say good morning to you and welcome to Nightside, gentlemen.
Good morning. How are you?
Doing great, and you all look wonderful. I should point out that when it comes to that sporting goods equipment, you were talking about golf clubs, the information that we received. We have to point out that's not the main reason you're flying in space, although some golfers would be flattered. First of all, a primary objective of your mission is microgravity science. Explain that for us.
Well, microgravity science is really just what people generally think of as laboratory sciences like physics and chemistry and biology and combustion science and material science that's done in space. And the reason for the micro means that there's a microgravity environment. That means about 1 part in a million of the Earth's normal gravity. And what that does is allow you to study things without the influence of gravity, which scientists have wanted to do for hundreds of years, and we're finally getting a chance to start doing that.
Your crew has been setting fires during these experiments, and it sounds a little scary. Now, what's the purpose, and can you explain the behavior of flames in the state of weightlessness?
I think I heard the question as, why are we studying fires up in weightlessness? And there's a couple of good answers to that. One is that it's really impossible to truly understand fires on Earth because of the fact that, to give you a simple example, if you light a match, you instantly create warm air, which rises because warm air weighs less than colder air. And that convective process of the warm air rising carries the fuel away from the fire and tremendously complicates the combustion process, making it difficult for us to really understand the basic physics and chemistry of combustion. And some of the experiments that Roger and the payload crew are doing up here will allow us to more fundamentally understand combustion, which is really important to our life on Earth. It turns out about 90% of the energy that drives our whole society comes from combusting fuels. And if some of the research that these guys are doing up here can improve combustion only 1 or 2%, that'll save billions a year to our economy and also result in less pollutants.
I want to ask you, Michael, what do you think about the Mars Pathfinder news? What's the reaction of the crew there?
Oh, we're all just tremendously excited about the Mars Pathfinder. It's a tremendous engineering accomplishment and a great tribute to the folks at NASA and the Jet Propulsion Laboratory. We also feel very privileged to be orbiting the Earth in the Space Shuttle Columbia during this historic occasion. I think that sort of symbolizes the synergistic role between humans and robots in space exploration. As it turns out, the Pathfinder and several robotic spacecraft that are planned behind it will help document the conditions on Mars in terms of the atmosphere and the planet's surface, and that information will help us design a spacecraft system that could carry humans to Mars in the future to help colonize Mars and the other planets. And so we're just tremendously excited about it.
Been reduced. Can you see the TV? Yes. It's 120 degrees away. Based on the grid squares, maybe even closer than that. The velocity is 0.0, okay. The jet is firing.
The Progress resupply ship has television cameras providing this view of the docking target at the back of the Kvant 1 module on the Mir space station.
It's about half a degree upwards of the crosshairs. The distance is about 4 meters. It's about slightly above the horizontal line than it should be. Well, it's going down now. It's all right. There is capture. There is contact.
have for LIF. I'm complete through steps B.27, and we'll wait for the experiment go time and the PCAP to continue.
Okay, Don, we copy that.
First column, 506 Echo, 8905, 118, 168, 5, 5, 1, 60, 1147, 2651, 1307. Second column, 614, 819, 164, X, Alpha, 10, 250, repeated 4 times. 5, 5, 2. I hope we have enough adjustment points in the switch here.
We think we do. We may actually have to adjust up. We're quite unsure about the smoke height on this one because basically it completely threw us off the map, that previous test.
Okay, I copy that, and I guess we're ready to go here. So thanks a lot for your words of wisdom, and look forward to this burn, and keep on talking to Ellen, who can talk to me during the burn so we can work it out.
We will, and thanks for all your help on this. We're looking forward to this one. This will be interesting.
It is going to be interesting, and put in a good word for me to everybody on the CM1 team. You guys have been doing a great job.
We think likewise in reverse. You've been done a great job for us thus far, and we thank you for your help.
Houston, we're ready for the downlink if you have it. All right, if you have it down there.
Yes, sir. We got a great view from the aft flight deck.
Okay, great. We have a little tape here, about 4 minutes long, with a nice variety of science and living in space stuff on it. So let me go to play, and we will start narrating the tape.
Hey, Jim, we just hit the K-band worm. How about holding up on the downlink for about...
First, here you see a scene of me back in the lab earlier today. One of my duties just about every day is to videotape Astro PGBA. This is part of the Express Rack, and the part that's of interest here are the plants that you see right here. Some of the screen is smudged. I think that might be some humidity on the camera lens, but beyond that, you can see some of the green plants growing. If I remember correctly, we have some sage, some pine saplings, some periwinkle, spinach is growing in there, and I would be hard-pressed to tell you which one is which. We also get several different views. This is another view of some of the plants that are growing in there. Over the last few days that I've been doing this video, I have been able to see that they are growing.
One thing people always ask us what it's like to live in 0G, and here I'm trying to demonstrate what it's like to try and sit down. What happens is that just you start floating away, and then you quickly get away from the thing you're sitting on, and you can't get back very well until you reach the ceiling. I think coming up next, I'm going to try and walk, and a similar sort of problem happens. So we need to modify the way we do things in space. Here you can sort of hold yourself down, but as soon as you let go, you quickly move away, and walking is not very practical. Every morning, we have to tape in procedure changes to our books, and so the first few times we do this, it is not quite as smooth as it is after a few days. Put the book down, the book comes up, put the book down, give it a good press so it stays there, the book comes back up, put the piece of paper down that's going on top of the book, give them both a press so they stay down, they come back up, and grab a piece of tape and try and tape it down quickly. As soon as you have a few things going on, it gets out of control. But we have things to help us, and so we reach for a bag and try and get out one of those things that will help us, and this is where anti-gravity comes into effect. It's not zero G, it's anti-gravity. Things come shooting out of packages as though they're being compelled by some other force, and we have to rearrange that.
Here I'm working on the large isothermal furnace. This is a facility built by the Japanese. This is the 4th time that it's flown in space, and I've had the great pleasure and honor of flying with it on 3 of the 4 times that it's been in space. This is one of the international experiments and payloads that we have on board. We have other ones from Germany, another major facility, Tempest. And these are two of our major partners putting together the International Space Station. I'm putting a sample in here for diffusion processes and molten semiconductors. It comes from my alma mater, Case Western Reserve University up in Cleveland, Ohio, and the PI is Dave Matheson. And we're looking at how certain impurities and dopants in some semiconductor materials, particularly germanium, which is of technological importance for electro-optic devices.
One of the things that's really important for the flight crew is to exercise in space. The lower part of our body doesn't get used in space like it does on the Earth, so you have to come up with inventive ways of stretching your muscles and working your muscles so that your muscles don't atrophy due to lack of use. It also, after a few days in space, we start to lose calcium in our bones, so it's important to put some force on your legs so that that can be reduced as much as possible. It'll take us a good 2 weeks to feel normal after we get back in space and be able to work out normally. The heart doesn't get as much use in space. It doesn't have to pump blood up to our heads, so it's very important for the flight crew to work out cardiovascularly every day. Otherwise, it would be hard to get the blood pumping up to our head on re-entry day, and it's important for the flight crew to stay awake.
Okay, well, that's our Crew Choice downlink for today. We hope that gave you a little bit better feel about what's going on up here. We'd like to take this opportunity to say hello to all of our loved ones back on the Earth who hopefully get a chance to see this. We miss you, and we love you, and we're looking forward to getting back home here at the end of the mission and seeing you again. Also, thanks to Mission Control for looking over our shoulder 24 hours a day and making this a successful flight. Thanks a lot. See you later.
Question. This is one of our rack-sized ones, the droplet combustion experiment. That's the volume where the droplets are burned. It's very carefully designed to rules the safety panel has set. We have clamps right where I'm pointing at that seal the chamber so you can open up to get inside to work, but it's very safe when the droplets themselves are burning. There's, of course, a lot of support equipment around that's also used during the runs. We have camera equipment. You see this camera here that's a high-speed film camera like you use for making movies that takes pictures of the drops while it's burning. We also have an electronics box that controls things, a camcorder, a Nikon F4 that takes all kinds of different pictures in different bands of the spectrum at different speeds. A recorder down there that saves all that data for post-flight analysis, and a laptop computer, just like we use in the orbiter, that allows the crew members to control all this equipment, like the power systems, from on board. The ground can also do some commanding for some of the runs, but this is how we do it when a crew is running the experiment. This whole thing, of course, is tied into the Space Lab systems. We have a little monitor here that allows us on board to monitor that the film is also sent to a monitor on the lab that goes to the ground. We have a monitor on the glove box that lets us see some UV images that are part of an internal camera that also run during the experiment. You can see we have lots of cameras taking data on these droplets.